how we can use the standard series when it comes to finding limiting values when the form is indeterminate. You know, when we are talking about limiting values, it's like when we are finding a situation, when we are in a situation like this, f over gx. At the end of the day, our answer came to this 0 over 0. You know, you might attempt to say, okay, it is 0, it is infinite, it is 1, or anything. But generally, in mathematics, we say this is indeterminate. And we always work further to make sure that we have a value for it. And one of the ways we can do that is by using standard series. Let's look at this one. Let's look at another place where we can use the standard series to work things out. Now, if I substitute 0 directly into this expression, what will it give me? It's going to give me tan 0 is 0 minus 0 over 0 cubed is 0 over 0. And you know what? That is indeterminate. And when we have an indeterminate situation like this, we try to work further to get a value for it. Now, if I should substitute the series we got for the expansion, the power series for tan x, let's see what that will be. So, we have the tan x to be x plus x cubed over 3 plus 2x raised to the power 5 over 15 minus x over x squared. And you know that this one is when x tends to 0. Now, at the end of the day, what are you going to have? This one and this one will cancel. So I'm going to have something like this. So I'm going to have 1 over x cubed into x cubed over 3 plus 2x raised to the power 5 over 15. Goes on like this. Now, let's cancel out this one. It's going to give it and goes on like this. So at the end of the day, I know x tends to 0. It's going to be 1 over 3 plus 2x squared over 15. Don't forget, x tends to 0. When we put x, when we put 0 for x in this place, all these other places will cancel out. So at the end of the day, our answer is 1 over 3. So you can see one of the applications of this standard series. It's very useful and in so many other situations. Now, we have a situation like this. If we put 0, 0, it's going to give us 0 over 0, and that will be indeterminate. Now, remember the expansion we got for this. S sine square x is equal to x squared minus x raised to the power 4 over 3 plus 2x raised to the power 6 over 45 and goes on like that. From here, you can work out the value for limit for sine square x over x squared when x tends to 0. So you can now say limit x tends to 0 sine square x over x squared is equal to x squared minus x raised to the power 4 over 3 plus 2x raised to the power 6 over 45 divided by x squared. Or I can bring the x squared in. If you work it out like this, to make it simple, let me make it like this. X squared minus x raised to the power 4 over 3 plus 2x raised to the power 6 over 45. Don't forget, x tends to 0. X tends to 0. Here, this one becomes 1. This one becomes square. This one becomes raised to the power 4. So it's going to be 1 minus x squared over 3 plus 2x raised to the power 4 over 45 plus. Now, if I should substitute 0 in this expression, we see that it's going to be 1. So the answer is 1. So you can see this is another place of applying it. It's just there are several places to put it to use, but this is just another one of the ways. I want us us to look at a way of finding limiting values when it is indeterminate. How do I mean? Assuming we have this function fx to be comprising of fx over dx. And at a, we have something like this, 0 over 0. We refer to this as indeterminate. How do we now find the value of the limiting value of this at x equals a or tends to a? L'Hopital came with a reasoning and said, okay, assuming we have this, and this is y, this is x, and we have it like this, and this one too, like this. Let's make this like this, and this is a. You can see. Let's make this fx. Let's make this gx. You can see that the two of them, when it crosses the x-axis, the y, the value of y is equal to 0. He now said, okay, fine. Let's make this a. That's x. Let's extend it a bit. And say, okay, let's extend it to h. So this place will now be, let's call this place k. Let's call this place p. Then f a plus h over f over g a plus h is going to give me hk over hk. This place over this place. Initially, when it crosses here, it is 0, 0. So, at this point, it's going to give me hk over hk. You can see, h over hk. Then, he now said that this value is also the same thing as hp over ap divided by hk over ak. The distance, okay. He now said is equal to hp over ah divided by hk over ah. You can see. And if h tends to 0, if h now tends to 0, that is, this h now tends to 0, that is g f a plus h, g a plus h, when h tends to 0, is going to give this h3 over ah, that is tan, it will be tangent of this place. You understand? It's going to be tangent of this place. Then we call this mu, and this place theta. Tan mu. And this one is tan theta. Okay. This smaller one is mu. It's theta. And if you look at this, it's equal to, when h tends to 0, it is giving us the first differential of a, because h tends to 0, and this one too, g at a. So what does that mean? It means that when you are finding the value of a limiting, when you are finding the limiting value and it's indeterminate, what you do next is to find the differential, or differentiate the numerator and differentiate the denominator, and the value that it gives you will be the limiting value at that point. If at the same time, that first time, it still gives you 0 over 0. You know what you will do? You will have to differentiate them again. And that will be over g one does not give you, continue until you get a certain value for it. Please note, this is only applicable when you have it as 0 over 0. If you have it as x over 0, so that is infinite. If you have it as 0 over x, that is 0. So that one is different. This is the only time you need to do all these L'Hopital's work. Let's look at one or two examples. Now let's quickly look at these two examples to close it. The first one says that we should find the limiting value for x cubed plus x squared minus x minus 1 divided by x squared plus 2x minus 3 when x tends to 1. The second one says x minus sin x over x squared when x tends to 0. Now let's see. So the first one we have x cubed plus x squared minus x minus 1 divided by x squared plus 2x minus 3 when x tends to 1. Now if I should put 1 in this place, it's going to give me 1 plus 1, 2 minus 2 divided by 1 plus 2, that is 3 minus 3, which is 0 over 0. So that is indeterminate. So what do we do next? We apply L'Hopital's rule. How do I do that? I differentiate the numerator and differentiate the denominator. So it's going to be 3x squared plus 2x minus 1 divided by 2x plus 2 when x tends to 1. So this is going to give me 3 plus 2, 5 minus 1, 4. 2 plus 2, 4. And that gives me 1. So the value of the first one is 1. So now let's go to the second one. It says x minus sin x divided by x squared when x tends to 0. So this is going to give me 0. What is sin x? 0 divided by 0. That is 0. That is indeterminate, sorry. 0 over 0. Indeterminate. Now, like the first one, we apply L'Hopital's rule. So, differentiating the first one, that is the numerator, I'm going to have 1 minus cos x divided by 2x. So, when x is 0, I'm going to have 1. What is cos 0? 1. 2 times 0, 0. And that is 0 over 0. Indeterminate. Again, like I said before, if we encounter this kind of situation, what do? We differentiate again. So if I should differentiate this again, it's going to be, what is differentiation of cos x? That's minus sin x. Minus times minus, that's sin x. Divided by 2 when x tends to 0. So 0 sin x, sin 0 is 0 divided by 2. You can see. So this is determinate. Our answer is 0. So the limiting value for x minus sin x over x squared is equal to